Hi, my name is Piotr Skowron. The main topic of this talk will be the concept of fairness. We'll try to answer the following question. How can we formally define what is fairness, and how can we formally reason about fairness? We'll specifically look at the setting where we have a group of individuals who need to make a collective decision. They would like to make this decision in a way that could be considered fair to all these individuals. In the first part of this talk, we'll consider a very particular model where we have a set of objects, preferences of the individuals over those objects, and our goal is to select a fixed size subset of these objects. We'll define concept of fairness and methods of reasoning about the fairness for this model. In the second part of our talk, we'll see whether these concepts and these methods can be extended to slightly different models. We will specifically look at the two models. The first one is of participatory budgeting, where a group of individuals, voters, need to decide how to split a municipal budget. That is, which projects should be accepted for funding and which should be rejected. The second model that we will look at is the model of making decisions over a set of independent issues. Here, for each issue, we need to make the decision, the binary decision, either yes or no. And there's a group of individuals, voters, who have their preferred outcomes. And the goal is to make these decisions so that the individuals should feel treated fairly. So let's first look at this first specific model that describes selecting a fixed size subset of objects. So in this model, we are given a set of objects, also referred to as candidates, and the cardinality constraint K. Our goal is to select a subset of objects, W, whose size does not exceed the cardinality constraint K. So we need to select exactly K out of those candidates, out of those objects. We are also given a set of voters, and each voter has preferences over the objects. So we can see that this model describes well many situations that we can find in our everyday life. Perhaps the most natural setting that comes to our mind when we think about this model is the setting of selecting a representative body for a group of voters, say a parliament. Indeed, here the objects are candidates running in election. Voters are those voters who cast their votes, and our goal is to select a specific number of candidates who will form an assembly, say a parliament. This model also well describes the situation of selecting winners in a competition. Here the objects are contestants or grant applications, and the voters are judges or experts who express their views over the qualities of the contestants or grant applications. We can see also that another application that fits this model is the problem of choosing locations for public facilities. Here the objects are potential locations of facilities, and the voters are potential users of the facilities who can express their views on whether they should prefer the facilities to be built. But we can see also that this model well describes the problem of presenting results in response to a user query by search engine. Here, the objects would correspond to potential responses to a query, and the voters could correspond to potential users of a search engine. And indeed, we would like to select a subset of responses that would fairly represent potential types of users and what do they have in mind when they type the query. For example, let's look at the picture in the right-hand side of the slide, which is a slide, which is a screenshot from my search of the word Apple. So we can see here that the Google search engine displays a set of images, and those images differ a lot. So we can see that among this set of presented results, there are pictures of a fruit, there are pictures of a logo of a computer company, and somewhere in the bottom we can also see an image of a cell phone which is produced by this company. So we can see that indeed those results are somehow diversified, and this set of the results in some sense represents potential types of users and what do they have in mind when they type a query Apple. Another example that fits this application, this model, is the problem of selecting validators in a consensus protocol such as blockchain. Here the objects, here the idea is that based due to efficiency issues, we would like to select a subset of users who would act as validators for transactions. And this set of selected validators should fairly represent all the users of the protocol, and here the preference relation could correspond to the relation of trust. So the main question here is how to select a subset of K objects which would fairly represent the preferences of the voters. And our approach would be to take ideas from political sciences and from social choice and see whether these ideas can be applied to our slightly more complex models. And from now on, I will speak about candidates instead of objects. So when formulating the model, I use the term objects deliberately in order to emphasize that the model is general and the objects do not necessarily represent humans, but they can also represent some physical objects like facilities or some abstract objects like content. However, from now on, just for the sake of concreteness, let's speak about candidates. I will also refer to a subset of candidates who satisfy the cardinality constraint as committees. So here our goal is to select a subset of candidates, a committee of candidates whose size is exactly K. Okay, how to define fairness? Let's first look at this very simple example where we have 8 voters, 9 candidates, and our goal is to select 4 out of those candidates. And let's assume that the preferences of the voters are very simple, so they are expressed as approvals. So for each candidate, a voter can say whether she approves a given candidate or not. So for instance, here we can see that voter V1 approves 4 candidates: green lady, the red guy, the green guy, and the blue boy. Voter V5 approves only 3 candidates, and voter V7 and V8, they approve 2 candidates, the orange guy and the orange lady. So I will also represent these preferences, these approval preferences, as such diagrams, where the candidates are represented as boxes, and with the following meaning, that each candidate is approved by those voters who are below the corresponding box. So in this example, which committee should be selected? So maybe the first idea would be to pick those candidates which are approved by most voters. So we can see that here the green lady, the red guy, the green guy, and the blue boy, each of them is approved by 4 voters, and each other candidate is approved by only 2 voters. So perhaps the first idea would be to select those 4 candidates which are approved by 4 voters. Would it be a good choice? Clearly, the first 4 voters would be very happy from this decision. However, half of the society would be disappointed because they could not find in a committee anyone that they would like. Okay, so let's look how this problem is solved in the problem of apportionment, where each voter votes for a single political party, and the goal is to distribute parliamentary seats among the political parties. So assume that each voter casts 1 vote, and assume that there are 3 political parties. The first party got 40 votes, the second party got 20 votes, and the third party got also 20 votes. And our goal is to distribute 4 parliamentary seats among those parties. So how should the parliament look like? So we can see that the proportional choice would be to give party 1 2 seats, party 2 1 seat, and party 3 1 seat. Indeed, such choice would be proportional because the number of seats given to each party would be proportional to the number of votes cast for this party. Okay, so from this intuition, let's look once again at our example. Which committee should be selected here? So we can see that we can group candidates in the voters so that these preferences could resemble preferences over parties, over political parties. So we can see here that the green lady, the red guy, the blue guy, and the green guy and the blue boy, they could be viewed as members of the same political party, and voters V1, V2, V3, V4 could be viewed as voters who voted for this party. Similarly, the sneaky guy, the pink lady, and the blue guy could be viewed as another political party, and the voters V5 and V6 could be viewed as voters who voted for this party, and so on. So taking intuition from the apportionment setting that we considered before, we can see that a much better choice, a much more proportional choice, would be to select 2 candidates from those who can be viewed as members of the first party, 1 candidate among those who are approved by voters V5 and V6, and 1 candidate among those which are approved by V7 and V8. And for example, a good committee, a proportional committee, would be the one that consists of a green lady, of the blue guy, of the red guy, and of the orange guy. Okay, so we can see how we could define what it means fairness, where those preferences are well structured. So we can see here that indeed the preferences were well structured in a way that the approval sets of each 2 voters, were either the same or disjoint. So then we could divide indeed the candidates and the voters into groups so that this preference profile somehow would resemble the political action over political parties, the instance of an apportionment. However, how to define it when the preferences are more complex and when the approval sets of any 2 voters can arbitrarily overlap? So in particular, if you would like to draw this nice diagram depicting this preference profile, we would see that this diagram would not look so nicely as before. And here, in fact, we do not have a good intuition which candidates should be selected. And definitely, we do not have a good intuition how to formally define what is fairness in this example, where the preferences are more complex. Okay, In order to answer this question, how to define fairness, proportionality, in the case of more complex preferences, let's move back in time and let's move back to the end of the 19th century. And also let's move back in space to Scandinavia. In the mid-1890s, two Nordic mathematicians, Thiele and Fragmain, were engaged in a somewhat heated academic discussion about voting rules. Sweden was soon to introduce universal suffrage, so the Conservative Party expected to lose majority in parliament and were pushing for an electoral reform. What was needed was a system, a voting system, that would guarantee a proportional representation. These two mathematicians came up with two different ideas. Thiele proposed a voting method which is now known under the name of proportional approval voting. According to this method, we look at each possible committee, that is at each k-element subset of the candidates, we compute the score of such a committee, and we pick the committee as the winning one, the one which has the highest score. The score of the committee is defined as the sum of the scores which are assigned to this committee by the voters. And the tricky part is how to define a score that a voter assigns to a given committee. The definition is a bit counterintuitive, namely, a voter V who approves T members of a committee, we assume that she assigns to this committee the value of 1 plus 1 over 2 plus 1 over 3 and so on up to 1 over T. That is, in other words, a voter assigns to a committee a harmonic number of the number of approved candidates within the committee. Let's look at this example. And for instance, let's look how, according to PAV, what would be the score of the following committee that consists of 3 candidates, the green lady, the red guy, and the blue guy. So we can see that voter V1 approves 2 members of this committee, namely the green lady and the red guy. So this voter assigns a score of 1 plus 1 over 2 to this committee. Voter V2 also approves 2 candidates from this committee, so she also assigns the score of 1 plus half. Voter V3 approves 3 members of this committee, all 3 members. Thus, the score that she assigns to this committee is equals 1 plus 1 over 2 plus 1 over 3, and so on and so on. And the total score of this committee is the sum of the scores which have been assigned to this committee by all the voters. And the committee with the highest score is announced the winning committee. Okay, now let's move to the Fragmain's proposal. So according to Fragmain's rule, each voter earns money with a constant speed of $1 per time unit. And we assume that buying a candidate costs N dollars, and the voters will use the money that they earn over time to buy candidates. Formally, in the first time moment, when there is a group of voters S who all have N dollars in total and who approve a not yet selected candidate, C, we assume that this candidate C is selected to the winning committee, and all the voters who approve this candidate pay for this candidate. That is, their budgets are reset to 0. Let's look at this example with 15 candidates and 6 voters. How the Fragmain's voting rule would elect committee in this example. And let's assume that the size of the committee to be elected equals 12. So in time t0, none of the voters have earned any money yet. In time 2, each voter and $2. So in particular, voters V1, V2, and V3, they're all together earned $6. So they can afford to buy a candidate. So according to the definition of our rule, they are also forced to buy this candidate. They select candidate, say C1, and they lose all their money. Okay, in time T2, voters V1, V2, and V3 managed to collect another $2 to earn another $2. Voter V4, V5, and V6, each of them has already $4, which does not allow them, any of them, to buy a candidate that they prefer. So the voters V1, V2, V3 altogether once again have $6, and they are forced to buy another candidate that they approve, say C2. Similarly, in time 6, in time T3 equals 6, these voters managed to gather once again $6, which allowed them to buy another candidate, say C3. But also in this time, voter V4 managed to earn $6, so she can afford to buy one of the candidates that she approves, say C7. Similarly, voter V5 can buy C8, and voter V6 can buy C9, and so on and so forth. And next, in time T4 equal 12, again, each of the voters managed to earn to gather $6, and each of them can buy one more candidate that she approves of. So, for instance, candidate C4, C5, C6, C10, C11, and C12 are bought by these candidates. So we can see that we already selected 12 candidates. The rule stops, and these candidates which have been selected, which have been bought by those voters, form the winning committee. So this winning committee in particular here is marked with the color on this picture. So which of these two rules is better? Which rule should be preferred? Both Thiele and Fragmain argued that their rules behave well for well-structured preferences of the voters. That is, when approval sets of any two voters are either the same or disjoint, then these two rules behave exactly the same way. Historically, PAV was preferred since it appeared simpler, and current research have so far suggested that PAV is slightly better in terms of proportionality than Fragmain. I will now briefly present two arguments in favor of PAV. One of these arguments is axiomatic in a way that we first try to formally define intuition behind proportionality, and then we will check whether this formal definition is satisfied, whether this formal definition of an axiom is satisfied by either of the two rules. The definition of this axiom can be intuitively explained as follows. Assume you have n voters, and we should select k candidates, then intuitively a group of voters of size n over k who agrees on some candidate, they should be eligible to decide about this candidate. Similarly, a group of voters of size L times n over k who all agrees on L candidates shall have right to decide about some L candidates in some L members of the committee. What does it mean to be able to decide about these L members? We define this as follows. So assume the k equals 4. So here this group of voters form half of the society. So they should be able to decide about half of the committee members that is about 2 committee members. So we say that the satisfaction, the average satisfaction, the average number of representatives that this group of voters gets in the elected committee should equal at least 2. Similarly, this group forms 1/4 of the whole society. So this group should be able to decide about 1/4 of the elected committee. And also this group agrees on one candidate, say the orange guy or the pink lady. So these voters, they should have on average at least one candidate in the selected committee. And formally, the definition is stated as follows. Each group with at least L times N over K voters who approve at least L same candidates should have on average at least L representatives in the elected committee. This property seems this property seems intuitively appealing. So let's ask whether it is satisfiable, whether there exists a voting rule and election system that would satisfy this property. And unfortunately, the answer to this question is negative. Let's consider this simple example with 12 voters. And assume that our goal is to select 3 candidates. Voter V1 approves AD, voter V2 approves A, and so on and so forth. So if we look at the first 4 voters, they form 1/3 of the society. They agree on candidate A. So according to our axiom, they should have at least 1 representative in the elected committee, on average. This means that candidate A must be selected, because if A wasn't selected, and even if we pick D and B, only the average number of representatives of these voters would be only equal to 1/2, which is too little according to our definition. So we know that candidate A must be selected in order to satisfy this property. Similarly, if we consider a group of voters V4, V5, V6, V7, we infer that candidate B must be selected. If we consider voters V7 up to V10, we infer that C must be selected. And by looking at voters V10 to V12 plus V1, we can conclude that also D must be selected. However, this is not possible since we only have 3 seats, seats in the committee, and we only can select 3 candidates. Okay, so we see that this property cannot be satisfied by any voting rule. However, what is very interesting is that if we relax this property just a bit and now require that the average number of representatives in the elected committee should equal at least L-1 instead of L, then this property is satisfied, and it is satisfied by PAV. What is interesting is that this harmonic function that we used for defining the scores in the definition of PAV is the unique function, is the unique way of defining score, which guarantees this property defining proportionality. Slightly later, it was also shown that Phragmein's rule satisfies even a weaker form of this property, namely if we replace L with L-1 divided by 2. So this result can be interpreted as follows, that Phragmein's rule is twice less proportional than PAV. Let's move to the second type of an argument in favor of PAV. This argument is based on the following idea. We'll first identify what it means for a committee to be fair under some simplifying assumptions for simple types of user preference or voters' preferences for which this concept can be, the concept of fairness can be defined intuitively. And then we will show how these concept can be extended to more complex preferences of voters in a principled way. As we already said, there are some types of voters' preferences where we can intuitively define what it means for a committee to be fair. And these preferences are those that closely resemble the structure, the party structure, and that closely resemble elections with political parties. Formally, we will say that that an instance is party list if for each two voters their approval sets are either the same or disjoint, because then we can group the voters and the candidates into these joint sets, and in this way we reduce the problem of selecting a committee to the problem of apportionment, which is well defined, well explored, and for which we can have very good solutions. For instance, we can here apply the DONT method of apportionment, which is used in many modern countries for electing parliaments. It is proven that this method has very good properties pertaining to fairness, and it is also it returns committees which are fair according to our definition, to our intuition. Okay. So we have this DONT method of apportionment, which specifies how to define fairness for these simple instances and how to deal with more complex instances. And now the idea is that if we assume that the voting rule, apart from behaving well for these simple instances, satisfies some other basic types of properties, then imposing those basic properties will uniquely extend this fairness to more complex domain. Let's see how this works specifically. We will define the following basic axioms. The axiom of symmetry says that an outcome of an election should not depend on the names of the candidates. So formally, it says that if for a given preference profile, we have a committee, a winning committee, then if we change the names of the candidates, then the outcome of the election should change accordingly. For example, here, if we swap the candidates, the green lady and the red candidate, then we will obtain another instance, and in the other instance, the winning committee should also consist of the pink lady and of the red guy, because this red guy was swapped with the red lady who was previously winning. So this is what the axiom of symmetry says. The axiom of consistency says that if we have two disjoint societies, and if these two disjoint societies agree that some committee should be selected, then if we merge these societies and run one election for this bigger society, then the outcome should be also this committee that those disjoint societies agreed on. And the axiom of continuity is a little bit more technical, and it is usually used in the literature to deal with to exclude some mechanism that strongly depend on tie breaking. It is defined as follows: assuming that we have two societies, and then there exists a possibly very large value z, such that if we multiply the first society, if we clone it z times, and if we add to this cloned election, to this cloned society, this second society, then this cloned society can dictate its will. So basically, this axiom says that a large enough majority of voters intuitively should have right to decide what is the committee, the winning committee. And this is a very interesting result, which says that proportional approval voting is the only approval-based committee rule which satisfies the axioms of symmetry, consistency, continuity, and non-proportionality. So in particular, it says that If we agree that those axioms, symmetry, consistency, and continuity, should be satisfied by our rule, and those axioms are very intuitive, and it seems that they should be satisfied by any good rule, then the only extension of the DONT method of proportionality, which is intuitive and which is well explored and which is used for selecting parliaments, the only method to extend this method of apportionment to the more complex setting where the voters' approval sets can arbitrarily overlap is to use proportional approval voting, is to use PAV. So the arguments suggest that PAV is a much better rule than the fragments rule. However, this conclusion will be too abrupt. Let's look at the following election instance, and let's compare the results, the committees returned by fragments rule and PAV for this election instance. So we can see here that the committee returned by fragments rule, the one made with color in the left-hand side of the picture of the slide, we can see that in this committee, voters V1, V2, and V3 decide about 6 out of 12 candidates. Those voters form half of the society and decide about half of the committee, which seems fair. This is not the case for PAV. There, those voters V1, V2, V3, they only get to decide. They only get to decide about 3 members of the committee. So why PAV makes this decision? We can see what happens here is that PAV observes that if C4 were not elected, and instead of that, if we elect C13, then the inequality in voter satisfactions would decrease. So indeed, voter V1 would get 3 representatives instead of 4, and voter V4 would get 3 instead of 2. And similarly, by removing C5 and C6 and replacing them with C14 and C15, the inequality in voter satisfactions would decrease. And this is basically, since PAV somehow its definition is based on the on comparing the satisfactions of the voters, PAV considers this a much better choice and goes for this committee. In a way, in the outcome returned by PAV, the voters V1, V2, V3 are punished for being agreeable and for agreeing to approve C1, C2, and C3. So we can see that in fact what happens here is that there is no a single way, a single type of proportionality. There are at least 2 different types of proportionality and of fairness. The type of fairness that is implemented by PAV is focused on welfare, on satisfaction of the voters. So in some sense, it tries to return a solution where the satisfaction of the voters would be in some sense balanced. While the proportionality implemented by fragments rule, it is more focused on voters' power, which is represented by this virtual money that they can use to buy candidates and to influence the decision which candidates should be elected. So far, we speak about axioms which formalize this welfarist approach to proportionality. However, in recent works, we also identified that there are different axioms which also describe the idea of fairness, but which are incompatible with the concepts describing fairness in the welfarist way. So there are two such axioms identified in the literature, and we will now look at one of them. This axiom is called priceability. So it says, we say that a price system is a pair that consists of a price P. This is the total price that needs to be paid for a candidate to be bought, to be included in a committee. And for each voter I, we have a payment function which specifies how money which are given to this voter, how they are distributed, how they are spent on candidates. So this price system must, so in order to call this per a price system, two properties needs to be satisfied. The first property says that a voter can pay only for candidates that she approves of, which is very natural. And the second property says that a voter can spend at most $1, which basically says that each voter is initially given $1, that is, it's treated equally. We say that the price system supports a committee W if the following conditions hold. For each elected candidate, the sum of the payments of the voters for this candidate needs to equal its price. Second, no candidate outside of the committee gets any payment. So the voters do not pay for a candidate which is not selected. And there exists no unelected candidate whose supporters in total have a remaining unspent budget of more than P, because if they had, then they could afford to buy this additional candidate to the committee. So we will say that a committee is priceable if it is supported by a price system, and we will say that a voting rule is priceable if it only returns priceable committees. So let's look at this example. For instance, here the outcome returned by fragments rule is indeed priceable. We can define the price system as follows. The price for a candidate to be selected equals half. And now we can define that, we can say that voter V1 pays 1/6 for candidate C1, 1/6 for candidate C2, and 1/6 for candidate C3. Additionally, it pays 1/2 for candidate C4. Voter V2 and V3, their payment functions are defined analogously. So we can see that C1 gets indeed the total payment of 1/2 because it gets 1/6 from each of these first three voters. And also C4, C5, C6, they get the payment of 1/2 from the one voter who approves them. B4 pays 1/2 for C7 and C10, and so on and so forth. And we can see that this price system witnesses that the committee returned by the fragments rule is indeed priceable. But the committee returned by PV would not be priceable, and in fact we can show a stronger results, which says that any kind of a rule whose definition somehow resembles the definition of PEV, which is defined in the welfarist way, that is, whose definition depends on comparing the welfares of the voters, any rule which is defined solely based on this information cannot be priceable. Last year, we defined a new rule, which we called Rule X, which shares the most appealing properties pertaining to fairness of PAV and of sequential fragments rule. This rule can be thought of as a variant of the fragments rule, where the voters do not gradually earn their money, but rather are given their money up front. So we assume that we split the total amount of n times k dollars among the voters. So each voter gets k dollars, and this amount of money is put in her virtual account. And now we gradually increase the cost per voter row. If at some step it happens that there is a still not yet elected candidate C, whose supporters could afford to buy it, provided that each of them would pay the amount of money equal to rho, then what we do is we do the following. We add this candidate to the committee, and we ask each voter who approves this candidate to pay the amount of rho, so that each of them, that they all together pay the total amount of $n for this candidate. And as I already advertised, this rule shares good properties of PEV and fragments rule. And it also nicely extends to other models. So now let's look at other models of collecting decisions. We will start with the model of independent decisions. In this model, we are given a set of alternatives. Each alternative is binary. That is, for each alternative, we need to decide either yes or no. And we additionally have a set of voters. And each voter has, for each alternative, has a preferred outcome. So we can see that this model is not exactly about selecting a fixed subset of objects. However, this model can be reduced to the model of committee elections. Indeed, for each alternative, we can define two candidates, one that corresponds to the outcome of yes, and the other one which corresponds to the outcome of no. And now the goal would be to select a subset of candidates of size m, but with an additional constraint that which says that for each alternative, only one of the candidates corresponding to this alternative can be selected, which means that we can select for an alternative a candidate that corresponds to yes, and at the same time selecting the one which corresponds to no. So this additional constraint makes things a little bit more complicated, but it appears that the rules that we defined previously can be defined also for this model, and they preserve some of their good properties. And another model, related model, which I would like to a little bit more elaborate on, is the model of participatory budgeting. According to this model, we have candidates, but each candidate has its cost. Additionally, instead of a cardinality constraint, we have a budget constraint, which says that the total cost of selected candidates cannot exceed the given budget. And here we normalize this so that the budget equals 1. And now here in this model, it makes more sense to refer to candidates as the projects. We also have a set of voters, and those voters have preferences over the projects, which specify which voters would like which projects to be selected. So let's look how this problem is typically solved in practice. So typically one uses a voting rule which counts the number of voters who approve each of the projects and select those projects which get the highest number of approvals until the budget is exhausted. So let's look at this fictional city of Circleville, which has the population of 400,000 people. And let's assume that the total budget that we can spend for this city equals $400,000. This city is divided into 4 parts, which are roughly of the same size. The north side is a little bit larger than the other parts, than the other 3 parts of the city. And now assume that we have a set of projects which can be realized in different locations. And now assume that all voters from the north side vote for approve the projects which are in the north side only. All voters which are in the east side approve only projects that are in the east side, and so on and so forth. So if this happens, then the rule would work. The rule would select the following set of projects: A, B, D, E, and I. So we can see that even though the north side population forms roughly 1/4 of the whole population of the city, it basically decides about almost the whole budget, and the other parts of the city that basically have no influence on how the budget is spent. So this problem is identified has been already identified, and what happens usually is that the budget is pre-divided, and different parts of this budget are assigned to different districts, so that those districts could decide how to spend their part of the budget. However, this is not a perfect solution, because still the same problem appears, but not in the scale of the whole city, but in the scale of the given district. Additionally, there are different types of other problems appear in this situation. For instance, let's assume that there are parents which do not which are spread among the city. So they are not assigned only to one district, but they live in different districts, and they would like to decide to buy one of the large playgrounds in the city. Then they have no possibility to express this preference, because they can vote only for projects which are in their districts. Additionally, a similar example, a different problem is with projects which are close to the borders of the districts, where voters from two districts would like to vote for them, since they would be able to use them, but they have there's no they have no possibility of expressing these in their preferences. Also, a similar example to the first one, let's assume that we have a group of cyclists who want a bike trail along the river, the example river that runs through the city, and again, they cannot express these preferences, because they cannot form a cohesive group that would vote for this bike trail, because they are spread among the city. So what we would like here rather is to have a voting rule which would be fair, but to all district groups, not just to predefined districts. So this rule should internally identify the groups of interests, let's say cyclists, by looking at their preferences, seeing that their preferences are cohesive, and should implement their will in a fair way. So what is interesting is that our rule X very well extends to this setting. Now we just split the city budget evenly among the residents of the city. And additionally, we can assume that the voters' preferences are more complex. They are not only in form of approvals, but that we can assume that the voters can express cardinal utilities, that is, values that quantify the level of appreciation for different types of projects. And also rule X would well extend to this setting. Then the change would be that now we gradually increase the cost per utility, rho, and at each step we check if there is a project C, which is not yet selected, whose supporters have enough money left to afford it, provided that each voter I would pay this value rho multiplied by her utility, the utility that she assigns to this candidate C. And if this is the case, then we also select, as previously select the candidate C, and ask the voter I each voter I to pay the price, to pay the amount of money equal to rho times her utility from the candidate. And what is interesting is that the properties of fairness that we described before in the context of the model of selecting a fixed-sized subset of candidates, those properties can be also defined analogously in this model of participatory budgeting, and rule X will also satisfy them. So we can see that those concepts that we know before, they were defined for a very particular model. However, those concepts extend and can be applied to models which do not, at first sight, do not very closely resemble the original model. So in summary, in this talk, we have shown, we have focused on the problem of proportionality in committee elections. We defined some rules which are proportional, and we defined some techniques based on axioms which allow to formally reason about fairness. And we also argued that these techniques and rules extend to other settings. And I would like to take this opportunity also to advertise our new survey on committee elections, where all these concepts and interactions between different kinds of axioms and different forms of proportionality are very well and thoroughly explained. Thank you very much.